Welcome to this exploration of the nature of truth. Today, we are going to move beyond the idea of truth as a simple fact and look at how it is constructed and verified across different domains. By the end of this lesson, you'll be able to distinguish between mathematical, scientific, and social truth, understand how large language models relate to consensus, rather than certainty, and explore the limits of formal systems. By the end of this lesson, you will be able to identify why something is considered true in a geometry textbook versus a biology lab or a court of law. Truth is not a single thing. It is a set of tools we use to navigate reality. Let us look at the three pillars: formal logic, empirical science, and social consensus. Let's start with the most rigid form, mathematics. In mathematics, truth is not discovered by looking at the world, but by following rules. We call these rules axioms. A mathematical truth is a statement that follows logically from a starting set of assumptions. If you change the assumptions, you change what is true. For example, in Euclidean geometry, we assume that parallel lines never meet. From this, it is an absolute truth that the angles of a triangle add up to 180 degrees. But if we change that axiom to describe the surface of a sphere, like the Earth, suddenly it is true that a triangle can have more than 180 degrees. In math, truth is conditional. If these axioms are true, then this conclusion must follow. We call this a formal system. In these systems, truth is binary. A statement is either provable or it is not, and it is exact. Unlike the real world, there is no probably in a mathematical proof. To deepen our understanding of mathematical truth, we must distinguish between two ways of looking at it: proof theory and model theory. Proof theory is about the syntax. It's like checking if a sentence is grammatically correct according to the rules of the system. In proof theory, a statement is true if there exists a finite sequence of logical steps leading from the axioms to that statement. We say the statement is syntactically derivable. Model theory, on the other hand, is about semantics or meaning. It asks, is this statement true in a specific mathematical structure? We call these structures models. Essentially, syntax equals provability, while semantics equals truth in a model. Think of it like this: the rules of chess are the proof theory. A specific game being played on a board is the model. A statement might be true in one model, but false in another, even if both follow the same basic rules. This distinction is vital because, as we will see, there are things that are true in a model, but can never be proven using the rules alone. For a long time, mathematicians believed that if something was true, it could eventually be proven. Kurt Gödel shattered this idea with his incompleteness theorems. Our goal today is to understand Gödel's incompleteness and the concept of independence. Gödel proved that in any sufficiently powerful formal system, like the one we use for basic arithmetic, there will always be statements that are true but unprovable within that system. Imagine a sentence that says, "I cannot be proven by these rules." If the rules could prove it, the statement would be lying and the system would be broken. If the rules cannot prove it, then the statement is telling the truth, but it remains unprovable. This is an undecidable statement. This leads to the independence phenomenon. Some famous mathematical questions, like the continuum hypothesis, have been proven to be independent of our standard axioms. This means you can choose to assume it is true, or choose to assume it is false, and both versions of math would be logically consistent. In summary, truth is broader than proof. This tells us that even in the most exact science, truth is not a closed book. There are horizons that our logic can see, but our proofs cannot reach. While mathematical truth is absolute within its rules, scientific truth works very differently. It is not about certainty, but about survival. In science, we never strictly prove a theory is true. Instead, we fail to prove it false. This is Karl Popper's principle of falsifiability. A scientific statement must be capable of being tested and potentially refuted. Think of scientific theories like biological species. This is the Darwinian analogy for truth. Thousands of ideas are born, but only the ones that fit the data survive. A true scientific theory is simply one that has survived the most rigorous attempts to kill it. We refine this survival using Bayesian updating. Here, P of H given E equals P of E given H times P of H, all divided by P of E. We start with a prior belief, P of H, and as new data comes in, we update our confidence. Notice the result. Scientific truth is provisional. It is a best guess that gets more precise over time, but is always open to being overturned by a more fit explanation. We don't reach a final destination, we just get closer to the target. Now we move from the lab to the community. Not all truth is found in a test tube or an equation. Some things are true only because we collectively agree they are. Social truth, or consensus truth, is created through institutions and collective acceptance. Think about money. A $100 bill is just a piece of paper or a digital entry. It has no intrinsic physical value like food or water. However, it is true that it can buy groceries because of a complex web of social consensus. If everyone stopped believing in the currency, that truth would vanish instantly. We see this in our legal and social systems as well. Rights, titles, and even certain identities function as social truths. They are maintained by a fixed point of agreement. I believe it because you believe it, and the institution enforces it. This is where worldview-dependent questions come in, such as modern debates over gender. Often, these conflicts are not about facts, but about different starting axioms. If one person uses a biological axiom and another uses a self-identification axiom, they will derive different truths from the same situation. Recognizing these as different axiomatic systems helps us understand why consensus is so hard to reach. We are not just arguing about the conclusion, we are using different rule books for what counts as truth. Thanks for exploring the nature of social truth with me. Finally, let's look at the newest player in the field of truth: artificial intelligence. Specifically, large language models like the one you are interacting with right now. An large language model does not know things the way a mathematician knows a proof or a scientist knows data. Instead, it generates a distributional consensus. It predicts the most likely next word based on a massive statistical model of how humans talk. If a large language model says the sky is blue, it's not because it looked outside. It's because in its training data, blue is the most statistically probable completion. This makes large language models incredibly powerful for social or linguistic tasks, but dangerous for deductive ones. They can hallucinate because they prioritize looking like a correct answer over actually being one. To solve this, researchers are developing neurosymbolic loops. In this system, the large language model acts as the proposer. It suggests a solution or a step in a proof. Then, a symbolic engine, a hard-coded logic checker, verifies that proposal against formal rules. If the logic checker finds an error, it sends the feedback back to the large language model to try again. This creates grounded truth. It combines the creative flexibility of neural networks with the rigorous certainty of mathematical logic. This loop mimics how human experts work, using intuition to find a path, but using formal tools to ensure they haven't stumbled. In summary, we have moved from absolute axioms to survival of theories, through social contracts, and into statistical probabilities.